welcoming home to SIGGRAPH two luminaries in computer graphics. This is a rare and special featured speaker talk, the Turing Lecture, given by 2019 ACM Turing awardees Ed Catmull and Pat Hanrahan. Woo! Pretty exciting. So Dr. Pat Hanrahan is a 3-time Academy Award winner and is the Cannon Professor of Computer Science and Electrical Engineering in the Computer Graphics Laboratory at Stanford University. In the shading languages and emergence of programmable graphic systems, Pat will review the history of shading languages and discuss the broader implications of computing and the future of computer graphics. Can't wait. And Dr. Ed Catmull is a co-founder of Pixar Animation Studios and served as president of Pixar for 33 years and serving as president of Walt Disney Animation Studios for 13 of those 33 years. He's a 5-time Academy Award winner and a dedicated ACM SIGGRAPH member for over 40 years. Isn't that cool? In the wild, unexpected, exponential ride through computer graphics, Ed affirms his early belief in the promise of computer graphics and takes us on a journey that leads to where we are today. So I am very excited to have ACM Turing Award laureates Ed Catmull and Pat Hanrahan take the stage to present 2 ACM SIGGRAPH awards that take us on a fascinating trip about their foundational and impressive contributions to computer graphics. So please join me in welcoming these 2 pioneers, Ed and Pat. Woo.
We're going to start this by presenting 2 of this year's awards. The first is the Computer Graphics Achievement Award, which goes to Michael Van de Pan for his fundamental work in computer animation, particularly simulation and control of physics-based characters. Michael's landmark I think this has got a mistake here. He wasn't alive then. Is 2007?
1993.
1993 paper on sensor-actuated networks reimagined both neural networks and reinforcement learning for graphics by using physics simulation to generate and validate candidate motions. His watershed paper in 2007 called Symbicon showed that robust biped gaits can emerge from simple constraints and was built upon and extended by many. His work since 2016 has helped pioneer the use of deep reinforcement learning for creating skill-based, physics-based agents. In addition, he has helped the field by co-founding the Symposium on Computer Animation, now in its 20th year. Congratulations, Michael.
I'd now like to present this year's ACM SIGGRAPH Practitioner Award to Paul Jeremias and Inigo Quiles for the development of Shader Toy and other contributions to computer graphics. Shader Toy is a tool for rapidly developing shader programs in a browser window using GLSL and the small but powerful vocabulary of functions extending it. Each month, Shader Toy is used by millions of people from virtually every country in the world. It is used by graphics practitioners, researchers, and teachers. It's even been adopted as a tool in industries outside the SIGGRAPH community. One reason for this broad user base is that Shader Toy is not just a programming environment, it also lets users see and build on each other's work. Learning new techniques in context, commenting on shaders allows the community to share ideas and insights. Browsing through tens of thousands of shaders helps inspire new ideas. Shader Toy is more than just a shading editing tool. It's a basis for vibrant and connected community of practitioners, researchers, and educators. and anyone interested in learning about computer graphics. Congratulations to Paul and Inigo. I'm first. My slides. So thank you, Elizabeth, for the introduction, and it's really great to be here in person. Ed and I, when we won the award several years ago, was right before the lockdown in California, and actually this is only like, I think, the second public talk I've given since then. But we wanted to hold out and give this award talk in person with all of our friends and colleagues. Let me begin by saying how humbling it is to receive this award. The only other person to receive a Turing Award in computer graphics was Ivan Sutherland. Ed was a student of Ivan's, and I worked for Ed at Pixar, and that's 2 generations of researchers. There's a whole generation of computer graphics researchers before me. They laid the foundational for our field. They also helped me with my early career and inspired me. I wish they would have been recognized too. Today I want to spend some time sort of telling you what I did, some history and context, and how I thought about various things as I did my work. So I was cited for my work in computer-generated imagery for the movies. Both Ed and I were cited for that. Here's a famous picture made at Lucasfilm, produced by Alvy Ray Smith. It's called The Road to Point Reyes. Probably many of you remember this. It's an old picture. The idea of this picture was to create a virtual view of the road to Point Reyes. So Point Reyes is a seashore, national seashore, in Northern California, near Lucasfilm. It was designed to convince George Lucas that computer graphics could make a realistic picture of an imaginary world, that CGI could create the diversity of what we can actually see in the world with convincing detail and complexity. So since receiving this award, I've realized actually the larger computer science community doesn't actually know much about computer graphics or what it takes to make a movie. They think it's magic. It is magic. But I've had to explain to people like what computer graphics is and what it takes to make a movie. And we needed to develop models and algorithms to create pictures of everything around us. And the whole SIGGRAPH community worked together for that for many years. We had to figure out how to make pictures of people, how to render people, places, things, teapots, bunnies, mountains, lakes, streams, and clouds, rainbows, halos, and glories. Cloth, and I worked on hair and skin. The whole community, it's not just Ed and I, the whole community developed literally hundreds of cool ideas that made it possible to make a movie. And this picture is just sort of an example of what an early day picture could do. Now, when we were at Lucasfilm, the goal there, since George Lucas was primarily doing special effects for his movies, was to be able to create computer graphics that could be seamlessly merged into live action. So this was an early test they did at Lucasfilm, young Sherlock Holmes, where you see the stained glass character in the church. And so obviously because of that history, the early days of computer graphics was very much about making photorealistic images, and that's what we primarily did, and that was our first goal. I'll come back to talk about that. But when I was there, we had a system called RAYS. So Lauren actually named the rendering system RAYS. It stands for Renders Everything You Ever Saw. So it was a funny little acronym. And we had these goals. We wanted to model the diversity of the visual world, all the various things we could see. If you walked outside, what could you see? We should be able to model that. And obviously we wanted a whole nother level of geometric and visual complexity. We wanted high quality with no artifacts, so we could composite it in with live action. And it turns out we always wanted to make it work efficiently in hardware. And by the way, you should, if you haven't read this great paper that Rob and Lauren and Ed, and Ed will talk more about this probably, wrote about the Ray's image rendering architecture. When I arrived at Pixar, they had already done all this work, all this amazing, innovative work. And then actually last year, Ed and I wrote a paper called The Design of RenderMan, which goes into other details about what we did there. And I mentioned hardware. I mean, this was a slide I made. When I got there around 1986, we actually had a retreat, and we had the raised machine goals. We were going to build a piece of hardware, and this actually is some of the details of that. One of the amazing things here is we wanted to render a scene with 80 million micropolygons, which at the time, if you bought a piece of hardware, it might be able to render like 40,000 polygons, so that's like crazy. And if you look at the total amount of computing that we would need, it was just sort of way beyond what we could do with the machines we had. So it really, unless we built hardware, we could speed this process up. It just wasn't going to be possible to do this. And if you think of this is in the 1980s. Actually, the last really movie I've seen where they've released good statistics, if other people working in studios have better statistics on this, you should let me know. Maybe I'll include it in my paper. But this is an example from Monsters University. And if you just look at it took 100 million hours of CPU time to compute this movie. And they were basically, if you do the calculation, they were using 1 petaflop of computing per frame. So that's about 1 million times more than our goal, okay? 1 million times more than our goal. And if you think about it, say 1983 to 2013, that's 30 years. And in 30 years, everybody sort of remembers Moore's law, Moore's law about performance. I'll come back to that. But it increases by roughly, computer power and computer capability increases by roughly a factor of 10 every 5 years. So if you do the calculation, 30 years gives you 10 to the 6 or 1 million. And so, you see that all this was enabled by increase in computing power. Now, what did I work on? So that was largely done before I got there. So what my job was to work on the shading language and the RenderMan spec. Actually, let me show you a little bit about me. This is me, 1983. I was a very happy grad student, because that's about 1 year after I discovered computer graphics. And I spent 1 year teaching myself how to program in C and Unix. I did not know how to program, and I decided because I wanted to learn computer graphics and implement stuff, I would learn how to program. And then I basically was working on implementing every paper in SIGGRAPH up to that time. I just systematically mowed them down one by one. And then I was sitting, actually, that was in a lab I was working in, and they had a graphics terminal there, an STC graphics terminal, which I'm sure nobody remembered. But I was sitting there all day writing software to implement various algorithms. So I was very happy grad student back then. And actually, this was my first project. This was a little before that picture was taken. It was the first tech report, actually I think the first paper I ever wrote, called Procedures for Parallel Array Processing on a Pipeline Display Terminal. And in fact, my advisor at the time, Len Ure, was super interested in neural nets. He was a computer vision researcher, and hardware. Okay, that was his main research subject. So this is not like a new thing, I guess. These ideas of building hardware and languages for that hardware is something that's been in my life since I started in graphics. Now, when I got to Pixar, there were these 2 great papers, and I want to give them credit. One by Rob Cook, 1984, and this was part of the RenderMan system, or the Ray system at the time, called Shade Trees, and then Ken Perlin image synthesizer. And they really came up with sort of the idea that if you had a rendering system, you should build some kind of language for it, or some kind of way of extending it. And so they really deserve credit for this idea, and I wish they would have got more recognition for it. But anyways, this sort of just jumping to the chase, this is sort of my language, or what I came up with at the time. And, obviously I don't expect everybody to read this, although if you like the code like I do, maybe you will. But anyway, nobody likes this picture of this corroded teapot, except me. I used to use it as my test example all the time. But anyways, the bumps on the teapot are generated by this noise function, and this is Ken Perlin's noise function, and you just add up 6 octaves of noise, and that creates this sort of like random bumpy texture, and then you use that to perturb the surface, and I'm not going to go through all this code, but then finally once the surface is perturbed, you compute the surface normals and you reshade the thing. So that's a typical like RenderMan shader. So really my contribution was just taking what Rob had done and building a complete language out of it, and then also figuring out how to implement it efficiently in software. So anyway, so that was the very early days of this. This is in the 80s when we were doing this. And to be honest, the main reason I did it was laziness. I mean, I had very demanding users, Bill Reeves and Evan Osby and John Lasseter and company, and they had a million ideas of what they wanted to do with the rendering system, and I had this long list of things they wanted me to do. I was maintaining Raise at the time, and it was a lot easier to just design this language and tell them, you go do it, than to go do all the things they wanted me to do. So it was a very much an expediency. So, okay, so around this time, same time, you start seeing, the emergence of graphics processing units and graphics workstations, which was around this period. And, one of my close colleagues and eventually became a PhD student of mine, Kurt Akeley, worked at SGI with Jim Clark. And actually, one of my favorite papers of his is the one on the reality engine, which was in 1992, I believe. And he basically came up with this, history of workstations at the time. Okay, so, in 1984, all you could do is draw wireframes. In 1988, you could basically draw shaded polygons. And I list some of the examples of early workstations that did this. And then in 1992, you got into full texture mapping. Okay, so it was very specific: wireframe, shaded polygon, texture mapping. And you see, it takes 8 years to get here. I mean, Moore's law is moving along, but this technology just did not get invented overnight. Now, I want to just mention, when I got to Stanford in 1995, that was the crazy, sort of the start of the GPU craze. And NVIDIA, in 1999, okay, so this is after that, sort of coined the term GPU, graphics processing unit. And they used the term GPU, if I understand it, for the first time a single chip implemented a complete graphics pipeline. So up until then, the chips might do rasterization, they might draw triangles, they might draw lines, but they did not do transformation and lighting, okay? So this was the first time an entire graphics pipeline was available on a single chip, and that's why they called it a GPU, graphics processing unit. Just to put this in some scale, and I'll come back to this at the end, this was made with 17 million transistors. Okay, we're now at literally 1,000 times as many transistors in a GPU right now. But it was quite an engineering marvel to get the entire up until this time, if you had a graphics pipeline like an SGI machine, it was multiple boards of chips, right? So this is like the whole thing on one chip. So that was a real breakthrough. Now, Kurt also, one of his, I think, most important pieces of work was the development of the OpenGL graphics pipeline, or the OpenGL architecture, which I just draw schematically here. I'm not going to explain this in great detail. I think everybody here knows that this is a simplified view of the original thing. But it's sort of interesting that Kurt developed OpenGL. Actually, Kurt and I worked together. Pixar and SGI around this time decided they were going to jointly develop a 3D graphics interface, and Kurt was representing Silicon Graphics, and I was representing Pixar, and we were very much like we were meeting every week and trying to do it. Eventually, we sort of split, and we split on extremely good terms. I mean, we just completely respected what each other was doing, and it turned out, and he explained. I remember him explaining to me one day, it's very different to develop a graphics library for a workstation or an interactive computer than for a rendering system. And if you read the design and RenderMan paper, I actually go through the differences. And actually, I think OpenGL, in some sense, has been way, way more influential than RenderMan because it literally runs on every one of our computers, or some descendant of OpenGL runs on every one of our computers. And so, so he came up with this specification. And what was really interesting about it and important about it is it was an architecture. And I just want to mention this word because it's really an important word. So he describes in his specification an abstract graphics pipeline. Okay, and an architectural specification like that is meant to be independent of any particular implementation. And I'm using Fred Brooks, who is somebody we all know and love, who also won a Turing Award, but not for his work on computer graphics, but his work on computer architecture, for his work on the IBM 360. But anyways, the idea of writing an architectural spec is you can implement in many different ways, okay, and it just sort of provides a blueprint for how to build it. And I'm not going to spend all the time on that, but as soon as I read this thing, I knew it was an architecture, and it's actually very similar to how a CPU instruction set architecture is designed. So it's in some sense laid down the foundation for graphics chips for many, many years. And of course, there's advances on it, like DX9 and DX10 and so on, that moved it beyond what he did. Okay, so those were the two things. I kept working on this after I left Pixar, and actually I remember writing a grant in 1995, and this is from my grant. I said, what I want to work on is what's beyond what we can do now. And it just seemed so completely obvious what to do next. Because, we could sort of, the nice thing about real-time graphics is it sort of lags behind by some number of years. Say, 10 or 20 years, what you can do in a software-only renderer on a CPU. And so we had done all this work on flexible lighting, shading, and texturing, like shading languages, and higher-level geometric pyramids. I'm not going to talk about that much. And then I actually said that, the next generation after that, this was 1995, might be ray tracing global news. Wasn't like that was that hard to predict. And I think it's actually sort of happening now, right? You sort of see chips that are capable of ray tracing right now. But these were not hard predictions to make, because we could just, imagine Moore's law running forward and taking what we had already figured out how to do and put it in hardware. So I wish I had a little more time. I am writing a paper. I have a draft of it where I go into a lot more detail what I'm talking about. But there was this period after this where people basically tried to come up with real-time programmable shading. And of course, the team led by Henry Fuchs and others at UNC developed the pixel planes and pixel flow architectures. And one of the first real-time shading languages was by Mark Lano and Anselmo Lastra. There was this system by Mark Piercy, SGI. We developed a shading language in 2001 called the real-time shading language. And then in 2003, Bill Mark and Kurt Akeley, both who I work with, and others at NVIDIA did CG, and then HLSL and GLSL got all created around that time. And I'm not giving this work the proper credit here because I don't have time. There was tremendous innovation. I mean, one general theme that I want to stress is taking techniques that we've developed in software that maybe even had hardware in mind and actually building hardware that implements it is no easy task, okay? And I wish I could spend a whole hour telling you about various things. I do want to mention one really important idea that came out of this, though. And there was this idea, and we still do it a lot these days, there's this idea of a multi-pass algorithm, right? You take the rendering system and you run your scene through it once, then you run it through it again, and you accumulate the image in some way, right? Then you run it through again, and you continually enhance the image. You add detail, you add shading. So this is an example of making a bowling pin by running 6 different passes of the bowling pin through the graphic system. And that was the idea that Mark Piercy and Mark Lano and others at SGI did when they wrote their paper on interactive multi-pass A. So I actually wrote a little equation here. You can sort of think of this like the frame buffer as like a register or accumulator. And then you just run some operation on it where you take what's in the frame buffer now and you add something in that's coming. And color stands for a color that came from a triangle that you're rendering. T stands for a texture. And you just keep doing this over and over and over again. And it looks like you're running a program, right? You're just executing these instructions and you're making the frame buffer compute what you want. And so this was a really appealing idea, and they were able to completely implement a shading language with it. But at the same time, all the graphics vendors were starting to come up with this idea of shader programs. And this was a little different. Instead of just running like a really simple instruction, like add something to the frame buffer or blend something to the frame buffer, they would have like a complete program that they were running. It might be a small program, 128 instructions, but it would take the inputs that came from the rasterization stage, run this program over it, and then store those as outputs. And this turned out to be a really important idea. And in one way of thinking about it is like if you do the multipass thing, it's like you're doing simple vector operations, like A plus B, where A and B are vectors. Whereas if you do the stream share program, you're doing a really complicated operation on your inputs. And the advantage of that is you do a lot more arithmetic compared to the amount of bandwidth that you spend. And if you know about computer architecture, bandwidth, memory bandwidth is always the limiting factor. And so this turned out to be a really important innovation and really became critical to developing programmable graphic systems, is this idea of shader programs. And we call that arithmetic intensity, this idea that you have to do a lot of computation. Okay, the last little piece of this puzzle, and I know I'm giving you a very short whirlwind tour of all this, but I worked on all these crazy things, was GPU. So the key thing here was actually a fairly simple thing. It goes back to my grad student days that I knew because of what I had done as a grad student. I knew people had been building parallel computers for many, many years, that there was this sort of simple data parallel programming model. And I knew about it. I'd programmed machines that use data parallel programming. Some of you may remember machines like the connection machine and so on. This was not a new idea. This goes all the way back to the beginnings of computing. And the thing about data parallel programming is since they had already worked it all out in some sense, is they had these sort of small set of primitives. Okay, so they had this primitive called map, which applies a function to a collection of things. And if you thought of like running a shader program over all the fragments generated by a triangle, you could apply a function to a collection of fragments, and that was equivalent to this map thing. Then there was this thing called filter, where if you have a bunch of things, you can remove a bunch of things. Okay, so that was a primitive. Then you had this gather thing, where you take you have memory and you give it an address and you gather in, and give data parallel programming, you give it a whole set of addresses and you gather them all in. But there were these two other primitives that GPUs weren't very good at, called scatter, whereas you just sort of write stuff to random locations, you scatter it all over memory, and reduce, which means you sum a vector up. But it was fairly simple that you could just imagine, well, we could tweak the GPU a little bit and it could do these things. And if we did these things, then we had sort of become equivalent to this general purpose data parallel computer. And so that was a fairly simple leap as well. And so, that led to the system called Brook that my student Ian Buck did in 2004. And it was just a really simple idea. You just said, let's make the GPU act like a data parallel virtual machine. Then you don't need to be a graphics programmer to use it. So people by this time had started experimenting with running different algorithms on GPUs, but you had to be a graphics programmer. If you wanted to run a program, you have to render a triangle. You have to learn how to use OpenGL or DX or something like that. So now you could just be like a molecular biologist, and you can now start writing programs like you might imagine you would do if you didn't know graphics. And then Ian actually went to NVIDIA and was the chief architect of CUDA, and they have several primitives. Many of you know about CUDA. They did a lot of obviously great things, but it basically became fairly general purpose parallel programming. So that was sort of like the final step. Okay, so we sort of arrived there. And I guess what I'm trying to say is we always were in incredible need of cycles, okay? And we needed to build parallel computers, and over a period of years, we just gradually made them general purpose. Okay, so there are two things I want to talk about, which I think are important little lessons. One is sort of domain-specific languages. So here's a couple slides I put together years ago. Is you can think of OpenGL as like a library. Again, whenever I see a slide like this, it makes me very happy because I imagine myself writing OpenGL programs and drawing stuff on the screen. Anyways, here's a simple OpenGL program, and it sets up a camera and draws a bunch of triangles and then swaps the buffer, and you go merrily on. Okay, so it's just a library, but you can think of this OpenGL as a language. I mean, there's actually sort of a syntax to it. Like, if you say GL begin, then you have to put colors and normals and vertexes in there, right? So I actually wrote out like a little grammar for OpenGL. So even though it's just a library, it acts like a little language embedded inside C, right? And so, and if you do things out of order, you don't obey this grammar, it'll give you an error. In fact, it can give you quite extreme error, might blue screen. Okay, so it's a language, right? And so it's like an embedded, what we call an embedded domain-specific language inside C. So anyways, so what's so great about this? Well, one is I teach graphics. You can teach people OpenGL or some similar system, in a week or two. It's fairly easy to use. It's at a high level. You don't have to know anything about NVIDIA hardware in order to use it. Okay, it's super portable. I mean, OpenGL runs on many different things, including CPU implementations, right? But it also runs on everybody's GPUs, and it's really fast, right? It just renders like unbelievably fast. So it's just really performant. And so what basically happened by using OpenGL as this language for programming graphics is we encouraged an incredible amount of innovation in the field. And we let ATI at the time and NVIDIA and many other companies explore radically different implementations of the hardware without changing the programming model. And that's something we had the advantage of that the people building CPUs never had, because they were always programming in C, an assembly language, and it was impossible to change the architecture without upsetting all the programmers because the tools would no longer work. So anyways, this is a really big thing, and this idea of using domain-specific languages for introducing new architectural ideas is now, I think, encouraged, and you see systems like Halide and others that follow this approach. The second thing that's really important, was a very similar idea, is domain-specific architectures. And this is a really important idea right now. In fact, mostly what I'm working on right now is hardware design. I'm building chips myself. I think it's a really interesting time to build chips. But why did I get interested in it? Well, we've all heard this end of Moore's Law. Now, as somebody in graphics that lived on Moore's Law for my whole life, the end of it is like an existential threat. If Moore's Law goes away, does that mean I guess I'm about ready to retire, actually. It might be time to retire, I might be time to retire. So, but anyways, what's happening is, eventually you get down where transistors, are they can't be smaller than a silicon atom, And we're getting pretty darn close, okay? You get down to about a nanometer or so, and you're getting there to the radius of a silicon atom, or a couple of them, or something like that. So this is a big problem, and of course you all have heard about this. It's a huge issue. We just passed a $50 billion, legislation to help try to deal with this issue. But anyways, you might think that's the end of the world, but in Hennessy and Patterson's Turing Award lecture, which is 2 years before ours, they actually thought this was going to be a golden age of computer architecture. And their basic argument is simply that, we used to only have one kind of computer, like an ARM computer or an x86 computer. Now we're going to build all these like specialized computers, and so it's going to be like, biology, but you imagine the Cambrian explosion where we go from only a few organisms to a planet full of teeming with life, with all sorts of interesting computing devices. So this is actually quite an interesting time. And just to show you how crazy it is, and you might all know this, here's Apple's M1 Max. Here's just a floor plan of it. And look at all the computing devices on this. This doesn't show, they don't tell you everything that's on it. There's codecs on it, there's compression chips, there's security chips, there's 8 normal cores, high performance cores, there's 2 low performance cores for doing I/O. Then there's this 2-core GPU on it. Now, I really like this picture, because notice that the GPU is significantly bigger than the CPU. And if you were to think of it in terms of compute power, it's enormously bigger. And this, I mentioned that the first GPU had 17 million transistors. This chip has 57 billion transistors on it. Unbelievable. Unbelievable. So what's basically happening is people are taking and building many, many different kinds of computers, optimized for different tasks. And I'll call those domain-specific architecture. And it's sort of quite interesting to conceive, like, where this is going to go. And I think a lot of this got triggered by GPUs, because GPUs showed that you could build a different kind of computer. Okay, so I'm out of time, basically. I have 1 second. Anyway, here's my summary. Let me just, I think most of the points I've made, hopefully, are ready. I just want to end with, graphics has really changed the way computer systems are built. The highest performing computers in the world are now GPUs. It's because, we can utilize an unlimited amount of computation in computer graphics. And we're just beginning. When you think of Michael's work on animation and reinforcement learning, that's going to even consume even more cycles. And not only that, the way we're doing it with domain-specific languages architectures is also the way other people are building their systems, like machine learning systems. And so it's actually, probably one of the most exciting times to be in computing, and I hope more people get interested in graphic systems in the future. Thank you very much.
Here in person. SIGGRAPH has been my home for over 40 years, and I have so many memories and friends here. This field has gone through a radical transformation over the course of my career, starting slowly, but accelerating as it in turn transformed other industries. I want to talk about the mad rush of these changes through the personal and limited lens of what I experienced. I originally wanted to be an animator, but frankly I wasn't good enough. So I switched over to physics. And this is at the University of Utah. As I neared graduation, I took a computer science course taught by Alan Kay. He blew my mind. This new field was thrilling. The problems were right in front of us. It was where I wanted to be. So I entered graduate school at the University of Utah to study computer science. The first class I took was taught by Ivan Sutherland. Talk about great luck. Alan Kay and Ivan Sutherland, these two teachers profoundly affected me, and both later received the Turing Award. There were several principles I learned early on. The first was from Alan, who articulated the implication of Moore's law. While no one believed at the time that it could last as long as it did, there was reason to think that it would continue long enough to lead to significant change. This was not intuitive, but Alan taught that one could follow the implications of exponential growth beyond what was practical, and then design for what was coming. I witnessed an incident in 1969 that made no sense to me. I was at an ACM conference when Alan, who was still a grad student, said in a speech that the speed and size of computers would reach the point where we could make a laptop computer. Remember, computers used several racks at the time. He showed a slide with a mock-up of what this might look like. It looked remarkably like an HT laptop that was to eventually appear many years later. It had a fold-up screen showing a CG image made at the university. After his talk, people lined up at the microphones to ask questions. One of these people was the president of ACM at the time. He attacked Alan for making such absurd predictions and said it was deceptive to have put the CG image on the screen of the mock-up. I don't know why he was so upset, but I learned that it is difficult, even for experienced people, to think about the implications of exponential growth, something that remains true today. I came away with the belief that I didn't want to be blind to this kind of change. Thinking about change became a foundational principle for me, one I used for the rest of my career. In grad school, Ivan taught me another set of principles. He had already made the foundational advances in graphics at MIT and built the first VR and AR systems at Harvard. Then with Dave Evans, they set up the computer graphics program at the University of Utah. He articulated a vision for computer graphics and then set up a step-by-step program for solving the problems in the context of this vision. Initially, the images were using polygons, and the computer images were very limited. We could only work on one scan line at a time. This limited, of course, to polygonal surfaces. The first step in their program was to develop algorithms to determine which polygons were visible in an image. John Warnock, who later founded that's another Jim. John Warnock, who later founded Adobe, was among those who created visible polygon algorithms. Another student developed an algorithm for making, that could be used for creating hardware to render the polygons in real time. The next step was to make the objects appear smooth, but the silhouettes were still polygonal. In Ivan's class, I realized I could combine my love of animation with the new field of computer graphics. So for my class project, I chose to animate a polygonal model of my left hand. I loved making it, and I wanted to add to the chain of advancements, so Ivan suggested that I find some way to bend the polygons at the silhouette. After a lot of thought, it became apparent that this approach was fundamentally flawed. I needed to render I needed to render curves directly, which needed far more memory than was available in the computers of that time. The only way I could approach it was to act as if the entire image of the Z-buffer, the entire image and the Z-buffer were in the memory. And since operatings didn't support paging in that era, I wrote a pager to move the chunks of the image in and out of memory. I even broke one of the disk files because it was rattling around so much. The disk, these were these great big disks at the time. But I was inspired by Alan's idea that you emulate the future with some confidence that at some time it will become practical. It was slow, but I could render B-spline patches, which led to texture mapping, because I now had a mathematically well-defined surface I could work with. The images were a big step forward, and others who followed kept adding to this chain of advances. The algorithms that we developed were both inspired by and limited by the machines we had. It seems like old-time talk to say how little the memory was or how slow the machines were, but it did enforce a kind of discipline. It's also true in the arts. You accept that you work within limits, and your challenge is to push beyond the limits, and when the boundary is moved, your challenge is to move on to other limitations. There was another project at Utah that I was proud of. The university sponsored workshops on the math of curved surfaces. Since I spent a lot of time thinking about curved surfaces, I knew there was a problem with working with a network of four-sided patches. The topology of the mesh did not work well with a natural object like a hand. I approached the problem by reverse engineering the math of B-splines into a set of geometric operations. These operations could then be applied to non-four-sided meshes as a rule for recursively subdividing the mesh. I proved this using just basic high school geometry, and I thought it was a great idea. So I showed it to a professor whose expertise was curved patches. He barely glanced at my 18-page handwritten proof, tossed it back at me and said, "Ed, what is this shit?" I was stung, but it wasn't part of my dissertation, so I set it aside. Later I showed it to Jim Clark. He implemented it, and we wrote a paper on it. Years later, Tony DeRose took it the next step, and we used it at Pixar for our films. We made it open source, and over time it became the primary surface patch used in the film industry today. Sometimes shit is worth it. Very early on at the university, I believed it would be possible at some time to create images with enough quality to be useful in movies. And a long-term goal, or a long-term vision, came into focus for me. It was a goal that I could organize my efforts around. Ivan supported this vision and tried to set up an exchange between Disney and the university, so he sent me to Burbank. It was amazing to visit Disney and meet some of the people who made the films I grew up with. But Disney had no interest in an exchange. They just wanted to recruit engineering talent to help design the new Space Mountain in Florida, a diversion I didn't want. Disney was the only studio in the industry that might possibly be interested in computer graphics, and I learned they had no interest at all. So I thought the best place to pursue my dream would be at a university. But there was a problem. At that time, computer graphics was not considered to be relevant to computer science. It was mostly just an interesting topic on the fringe. There were very few university programs interested in computer graphics, and at two of them, Cornell and Ohio State, the programs weren't even in the computer science department. When I interviewed with schools, I tried to explain the long-term potential for graphics, but no one thought it was important. I could not get a job at a university. Then at the end of 1974, I received a call from the president of NYIT. He was not technical, but he wanted to make animated films and believed that computer graphics would become important. That was the good news. The bad news was that he thought that computer scientists would replace the artists. NYIT was willing to buy 2 full-color frame buffers, which cost $180,000 each. Excuse me. We had more memory for imagery than anyone else in the world. We were ready to get to work. Alvy Ray Smith, who was the second person to join me, had been frustrated by an odd view about color at Xerox PARC, but now he could write a full-color painting system. I wrote a 2D animation system in a couple of 3D rendering programs or systems. We brought in people from all over who shared this vision. I was new at managing, and I wanted to replicate the environment I'd experienced at Utah. A vision, a culture of sharing, and support for what would be a long step-by-step process. This was something I wanted to carry with me wherever I went. Since it would take many years to reach our goal, I didn't think it would be helpful to think that our advances should be or could be kept secret. I believed the best approach was to participate in SIGGRAPH, hire people smarter than me, and publish everything we did. It was one of the best decisions I ever made. After 5 years at NYT, we came to believe that our main weakness was that we didn't have any real storytellers. And we couldn't succeed without the kind of people who would benefit from the tools we were building. We made some visits to studios showing the imagery, and they were very impressed with it, but they had no interest. Everything changed because of a single movie, Star Wars. George Lucas wasn't technical, but he saw what ILM was able to accomplish, and he believed that computers would play a role in the future of filmmaking. For the first time in the film industry, someone with credibility was willing to invest in it. So in 1979, I left NYT to start the computer division at Lucasfilm. And it became a magnet for people interested in advancing the industry. Alvin was the first to join, and he led the graphics group. George was ambitious because he wanted to change 3 aspects of filmmaking: special effects, video editing, and digital sound. We dived into all 3. He based his company just north of San Francisco, which meant we had about an hour drive to Silicon Valley and an hour plane ride to Hollywood. This was a great location. We had good access to these 2 areas, but with a moat. It's very helpful, actually. We were very happy to have that distance. Fortunately, George supported our decision to publish and participate in the broader community. One of our competitors bought a $10 million Cray 1 computer. We did a back-of-the-envelope calculation, and based on the assumptions about what it would take to make a feature-quality movie, we would need the computing power of 100 Cray 1 computers, but at 1/10 the cost of just one. Based on where we were on the exponential curve for computing speed, it would take another 14 to 15 years. Our time and resources were better spent on the many problems we could see here and now. If we're going to go on and follow up on some crazy-ass vision, we needed to have a clear-eyed vision or view of what the problems were and what our steps needed to be. Coincidentally, when we completed Toy Story about 15 years later, we were very close to our estimate about the computing power required. I really value the process of working through the implications of coming changes. Working with film resolution images required that we design and build a system to hold an entire film resolution image in the computer, and it would require far more processing power than was available in the workstations. This led to the creation of the Pixar image computer. On the rendering front, Lauren Carpenter developed a new renderer that could handle high complexity, which he named Rays, as Pat just pointed out. Rob joined us after significant advances in lighting and shading. The 3 of us met in my office at the whiteboard to try to define what our big goal should be. At this time, since the state-of-the-art was around 40,000 polygons, we went through the calculation that Pat showed to come up with this number of 80 million. I don't know why we didn't round up to 100 million, but it was just what the popped out of the calculation. This is what it would take to meet the high standards of ILM and that was our goal. We were going for crazy complexity, as well as for motion blur and depth of field. We wanted an outrageous goal to force ourselves to think about the problem in a very different way. It led to a series of insights that changed rendering. We started with Lauren's architecture for complexity. Rodney Stock, a hardware designer working with us, proposed we consider point sampling similar to the dithering that's used in printing. Rob ran with this and experimented with various techniques for Monte Carlo distribution of the samples. Ultimately, he came up with a brilliant approach for the distribution, or the sample distribution. Tom Porter came up with a key insight to spread the samples out over time, solving the motion blur problem. He implemented this to create an image of billiard balls in motion with the ball set to read 1984, the year in which this was done, incidentally. Then Rob rewrote everything to create a clean structure that was object-oriented, enabling the software to evolve as we developed new techniques. We knew it wouldn't be practical unless computing power increased by at least 100, but we knew it was coming. Alvy conceived of a short film to demonstrate all we were doing at Lucasfilm, Andre and Wally B. John Lasseter joined us to animate the characters and bring something to them that only a good animator can bring. It was a thrilling time when remarkably creative people pushed the boundaries on many fronts. Things began to change at Lucasfilm, though, and near the end of 1984, George found it necessary to sell the computer division. The following year was brutal, but ultimately Steve Jobs bought the computer graphics division, even though George told him we were hell-bent on doing animation. Pixar, the company, was born. Incidentally, Steve never questioned my decision to publish everything. Steve is known to be very secretive, but he understood our reasons for full and open engagement at SIGGRAPH. Bringing in great people was much more important than any particular advancement we made. Now, we were in the business of manufacturing and selling special purpose computers, something I never foresaw. And none of us, including Steve, had any experience either making or selling high-end hardware, which meant that we would make many mistakes. We brought in manufacturing people, and we wrote software for contracts, in particular one for Disney, which is where they wanted us to color hand-drawn cells. To my surprise, I learned a great deal when we began manufacturing. I previously thought that manufacturing was rather mundane. I was wrong. I learned long ago, though, that I'm wrong about half the time. And this was one of those times. The process Toyota used to involve people at all levels of manufacturing was fascinating. Not everything that happens is the result of some big breakthrough. Often it's the result of a large number of small changes. As a business, though, we were failing. There was no way we could compete with the accelerating drumbeat of Moore's Law. This underlying dynamic kept everything changing, catching even people who should know better off guard. It was time to get out of the hardware business and focus on software. In doing so, we wanted to maintain Disney's trust, but the software that we wrote for them only ran on our hardware. So we sold the hardware business to another company, enabling someone else to make the images. We entered into another contract with Disney to port the software to Silicon Graphics, which by this time had enough capability to do the job. The trust we earned with Disney by doing this paid off later, but that's another story. Jim Clark, another Utah graduate, had founded Silicon Graphics using the geometry engine, a precursor to GPUs. At this time, the workstation companies were in a heated competitive war. The Pixar the Pixar renderer was the best for high quality, but it was difficult to use. Jim approached me proposing we should jointly design a rendering interface for the industry. 19 companies joined in this process. One decision I feel proud of was that we asked Pat Hanrahan to be the architect of the design. Pat gained everyone's confidence because he was a good listener, a great designer, and highly respected. Not only was the design clean, but he built on Rob's concept, as he talked about, to build a sophisticated shading language. All of this was to make rendering more accessible to people. This was the RenderMan interface. In the broader community of SIGGRAPH, new advances were published every year. For many years, the holy grail was photorealistic images. But graphics research broadened to include modeling, simulation, and complexity. How do you model and render the flow of water, or cloth, or hair? How do you simulate natural phenomena? And very importantly, how do you control the simulations to meet the needs of story? It was exhilarating and inspiring. Then the effects industry began to embrace computer graphics. One of the cool things about the effects industry, starting with ILM, is that they don't have any preconceived notions about how things should be done. They were not fixated on what they had mastered. They just cared about what they could get on the screen. If you came up with something better, they would use it. 1991 was a pivotal year. Terminator 2 was released with the major character being CG. Beauty and the Beast was released with 3D, the 3D ballroom sequence, and Pixar signed a deal with Disney to make Toy Story. By this time, the pace of advances was increasing, as was the speed of computers. In 1993, Jurassic Park was released, which signaled to the film industry that everything was about to change. Followed in 1995 by Toy Story. 91 to 95 was when the industry went through a discontinuity, a significant change in the acceptance of technology. Of course, from our point of view, this discontinuity was the result of many years of work. In this same period, the games industry started to enter the picture. 3D games were still crude, but the performance had reached an impressive level of performance, and John Carmack was pushing the edge to get 3D games on the PCs. NVIDIA was founded in '93, and it began manufacturing chips. Pat showed pictures of it. But at some point, they reached an existential moment, and they designed and built a chip in 6 months. And it started a culture at NVIDIA centered on a goal of releasing a new chip every 6 months, an unheard of release cycle. AMD was a competitor, reinforcing the rapid cycle for increasing GPU performance. Meanwhile, SIGGRAPH had a body of research in algorithms, lighting, and simulation, all of which the games industry wanted. NVIDIA could draw from all of what was known, trying to meet this insatiable desire for speed and realism from the growing graphics industry. SIGGRAPH and the rest of the academic and entertainment industry were nowhere big enough to generate specialized chips, but the games industry was. The GPUs were put into workstations, giving graphics researchers faster machines for algorithm development, leading to more papers at SIGGRAPH. This was a cool cycle between games, GPU companies, and the SIGGRAPH community, leading to a rate of increase in computing performance that increased that of Moore's Law for several years. It was a kind of virtual cycle with nobody in charge. Around 2009 to 2012, it became clear that GPUs were useful for problems other than games. Those matrix multiplications needed for simulation were useful in many areas. So people began to use them in scientific applications. In particular, neural networks, initially conceived more than 50 years ago, became practical, leading to deep learning, which is now having a major impact across many industries. This was an unplanned and completely unexpected surprise, arising from the GPU games academia cycle. Computer graphics started off marginalized, but has gone through an unpredictable, wild roller coaster ride as it moved from the fringe to be an important part of many industries and computer science. That ride will continue, as will the high rate of change. It is difficult to imagine where it will take us, but much more is needed. We need audacious goals to help us reshape our thinking. I can only tell bits and pieces of what I experienced, but I know I have been well served by the principles that I was taught. Well, part of this narrative highlighted exponential change and the importance about thinking about the implications of that change. There's something even more important to me. I stand in awe of the teachers, the mentors, and the colleagues I have worked with. I am grateful for their values, their thoughtfulness, and their passion to make a difference. Thank you very much.
What do you think, huh? It's pretty amazing. Let's give them another round of applause. I was taking notes, and I'm just so inspired by all of the words we heard, but I think the one thing that kind of summarizes why we're here and what's been done in the past is emulate the future, and in time it will become practical. And so on that note, I wish everybody a good day, and thank you very much for coming. This is just fantastic.